R.I.P. Krypton. What was Jor-El's calculation? So, first of all, I better admit that I'm a little biased towards the Richard Donner original Superman movie from 1978, and for pretty good reasons. It was a great movie, especially in its day. But of course, many of these concepts also relate to the cartoons, the original comics, the radio show, the TV show. Well, I guess lots of TV shows now, huh? But in general, what I'm sticking to primarily is the original Richard Donner Superman movie. Now, Krypton went bye-bye. Krypton, I hope that's not a spoiler. Krypton blew up. And Jor-El, Superman's dad, knew it was going to blow up. So how did he know this, whereas other people did not, other Kryptonians? This is the first page of the first issue of Action Comics #1, when the character was introduced. And there's some interesting things here. Like, first of all, when they talk about his planet, what all they really say is it was destroyed by old age. So the Earth better look out, because it's pushing 4.6 billion. So I don't know. Another funny thing about this, other than the fact that they try to explain his powers scientifically, see there at the bottom with all the insects, they also have him amazingly able to jump 1/8 of a mile. So that would be about 660 feet, or about 200 meters. So that was the amazing thing at that point in 1938, that he could jump 200 meters. Not fly, just big jumps right over a 20-story building. The word Krypton, at least in English, originally was applied to one of the noble gases. So why were they called this? Well, nobles, like nobility, are kind of born lucky. They don't have to work for a living. They don't have to interact with the commoners, the peasants. And noble gases are just like that. They sort of float around in their own little world, never having to interact, engage in chemical reactions, or do any of the things that all those other elements need to do. I guess neon is the epitome of this, as well as argon. But Krypton is the one that we're here to discuss because of the name. Okay, Xenon, just a weirdo. Doctor Strange, Dr. Xenon Bloom. Here's where the noble gases are located on the correctly formatted periodic table. They're a little family, pretty important family, way off on the right-hand side, even though technically the periodic table sort of spirals down. But that's the way we often think about it, and they all have a lot in common. You can see Krypton in a spectral bulb, glowing, producing its spectral lines. That's pretty much what you can do with it. It was discovered in 1898, which is interestingly 40 years before the first Superman comic. So the element was coined 40 years prior to the first use in Superman. And the name of the element, Krypton, means hidden in Greek, like cryptography, crypt, things that are buried, hidden, okay? Because they wanted you to know, like many element names do, how hard it was to find this one. Some of the noble gases, they just popped right out of the air, like argon, but Krypton took a lot longer. It was a little harder to find, and they want to make sure you always remember that. Okay, so never forget the trouble they went through to isolate Krypton. Another name that sounds similar is kryptonite. Okay, kryptonite is, of course, a fictional mineral which presumably would contain krypton, but krypton doesn't usually typically form bonds, although it might be able to be forced to under certain circumstances. Or maybe it's just called that because it's a mineral from the planet Krypton, having nothing to do with the element on the periodic table, krypton. It's supposed to be green, although in the comics there's many other variations that have many other effects on Superman. And so kryptonite is interesting because it was coined in 1943, I guess 5 years into the run, and it was a combination of the word krypton and the word meteorite, or the suffix for meteorite. But as I understand it, kryptonite did not first appear in the comics or the TV show or the cartoon. I think it originally appeared on the radio show, on the radio drama. So interesting how some of these things that become so iconic originate in other media than the comic book itself. As I understand it, the first time he ever flew was also in the Fleischman cartoons in the 40s. So before he was flying in the comic, he was already flying in cartoons. Before he had kryptonite in the comic, he already had kryptonite in the radio show. Go figure, right? Here we see the former planet Krypton orbiting its red star, Rao. So what is it about that star or about that planet that caused the destruction of Krypton? And what exactly were the calculations that Jor-El did? So to understand that, we've got to talk about Krypton, the planet, and what happened to it. Now, Krypton was a more massive planet than the Earth because it had a higher surface gravity. So the only way to easily get a higher surface gravity is to have a more massive planet. The other way would be a denser planet. But there's not too many materials that would give you a higher density than the Earth, for example. So it was presumably a bigger planet, and then that planet could trap various things in its atmosphere. But what concerns us is, how did it fall apart? What happened to it? Krypton, at least in the movie, is portrayed as a frozen over world. Now, obviously those crystals there could be silicates or some other mineral, but it does give the impression of being frozen. So the obvious assumption is, oh, that would be, water ice in addition to whatever silicates underlie it. But clearly it's presented as a cold place in the universe. Now, the temperature is never given. You never see a thermometer, for example. So presumably it would be temperatures similar to, I don't know, like Antarctica, perhaps. In the council meeting after the trial that banishes Zod to the Phantom Zone, Jor-El mentions that he has concluded that Krypton will be destroyed in 30 days, in less than 30 days. It turns out to be like seemingly the next day, but another scientist responds that she has concluded that Krypton is just shifting its orbit. And I can sort of see both sides of this. I can see why both of them might have reached that conclusion, if my hypothesis is correct. What were his calculations, though, that led him to this conclusion? What was he calculating? What was he thinking about when he decided, I think this planet's going to blow? Now, he did promise that neither he nor his wife Laura would leave the planet, but he very cleverly excluded his newborn son from that promise. And so he was able, through a legal loophole, even though he would never violate the laws of Krypton, to save his son and send him off in a spaceship. Seems kind of cold-hearted, but I guess Kryptonians were just like that. They were literally and metaphorically cold people. He preserved the knowledge of Krypton in a crystal, which presumably acts like a computer, and educated his son remotely. They managed to launch the spaceship just in the nick of time as Krypton began to fall apart around them. As seen in the movie, very, very clearly, it's collapsing all around them. When Krypton finally does explode, the only thing in the movie that sort of goes against my hypothesis is that they also had the star Rao explode at the exact same moment, which I don't know how that makes sense, but I think it just looked more dramatic than just having the planet explode. They had the planet and the star explode. But I think that was just overkill. And it doesn't negate my hypothesis, but it just seems like that was a little bit extra thrown in there. I don't know. To understand stars, we use the HR diagram, the Hertzsprung-Russell diagram, and it classifies them by their brightness. The brightest ones are at the top. And by their temperature, the hottest ones are on the left. Now, if you watch a star over its lifetime, it changes its location on the HR diagram. It can get hotter, it can get brighter, it can get dimmer, it can get cooler. It moves around. It turns out the color is related to the surface temperature of the star, not the internal core temperature, but the temperature of the surface. And so it turns out that the reddest stars are the coolest stars, which kind of makes sense if it's a cold planet. Maybe it's just not getting as much energy from its cold star. But if I show you our sun's life cycle on the HR diagram, maybe you'll get some idea about how stars can change over time. Notice that it says beginning life as a nebula down on the lower right. Okay, then it's going to pop onto the main sequence where 90% of stars exist. And watch how our sun has changed and will continue to change over the course of its approximately 10 plus billion year lifespan. Joins the main sequence. Then this is where it is now. In the far future, it will expand to a red giant, red there. Then it would blow off a lot of its mass into a planetary nebula, and then essentially it would just be cooling off. I'm keeping it that color so it can highlight it, but it basically ends as a brown dwarf cooling off in space, getting dimmer and dimmer, redder and redder, and eventually very little light would be emitted whatsoever. So just like that sequence, that stellar evolution of our sun, Rao would have had something like that, although it probably wouldn't have gotten as far up the main sequence, depending on whether it's supposed to be a red dwarf, okay, not the BBC red dwarf, or a red giant. But in any event, it's a cooler surface temperature star, so it's not giving out as much radiation per surface area. You can sometimes make up for that if the star has a big surface area, if it's just a red giant or red supergiant, or if the planet is close enough to the star. But essentially the idea is because our sun has a higher temperature output, that is what is energizing Superman here on the planet Earth. So there is the path that our sun follows in the course of its lifetime, just to show you that stars can change on this HR diagram. They change over time. Another thing to consider is that planets are formed around their star of similar materials, but there's one problem. Not everything that's in the nebula can go into the planets. The complication is that for something to sort of stop, be sort of waylaid, on its way to the center of the nebula, it basically needs to form some sort of a clump. Well, gases do not do that. So the only way to do that is to have solid material aggregating together, what they call planetary accretion. So what you really need are things that are solids in the nebula. Okay. Once you get a big enough solid, let's say nucleus of the planet, well then it has gravity. That gravity can trap some of the nebula around it as an atmosphere. But you need something solid, otherwise it's going to just head to the central star when the star was forming. So in a nebula, when a star is forming at the center, what you find is temperatures are cooling off as you move away from the center, but the nebula is also thinning out as you get away from the center. So there's a trade-off between the cooling temperatures, which make more things solid, and the thinning nebula, which gives you less of all the materials you need to make a planet. So it's this trade-off that causes the various kinds of planets that we see, especially the ones we are very familiar with in our solar system. If you look at the materials that you can make a planet out of, it's heavily dependent on the conditions in the nebula when the star was first forming. In our solar system, the inner planet Mercury pretty much had to be made out of iron. That's why it has such a large iron core. When you get to Venus and Earth, incorporating silicates, think of most rocks, was it something that could be solid, making the planet significantly larger. But even by the time you were at Mars, those materials are kind of thinning out a bit. Mars winds up being a little bit smaller. Then the leftover bits form all those asteroids, which don't even add up to half of our moon. If you put all the asteroids together, it's not as much as people say. The big important thing I wanted to get to, though, is after the asteroid belt, we had the freezing point in the solar nebula. That's where we could have ice. When you could have ice, boom, that was a major factor in making planets bigger. So if Krypton was a bigger planet, well, it probably incorporated at least some ice into it. Now I'm talking about water ice, of course, but there's other kinds of ices. There's methane ice and, of course, dry ice. Dry ice is carbon dioxide in solid form. So what we find is that our outer planets are so much bigger because they were able to incorporate ice into the core of the planet, giving them more gravity. And then with that greater gravity, they trapped the solar nebula around them. They were also farther away from the star, so not as much of the atmosphere was blasted off over the course of time and from fusion ignition as well. So basically, inner planets in our solar system are made primarily out of rock and silica. They don't have a lot of ice. Even though we have an ice cap in Antarctica, in Greenland, Mars has ice caps as well. That's not a lot of ice. That's just on the surface. And if you look at the much, much larger outer Jovian planets, well, the reason they're so big is predominantly because of the impact of ice. Now, even though people like to describe water as being scarce in the universe, it is the third most abundant molecule in the whole universe. So it is not scarce. The scarcity comes when you're looking for water in the liquid form. And then, of course, the Jovian planets, what we see of them is their outside, which is a lot of the solar nebula that they trapped with their gravity. The Jovian planets, by the way, we've gotten away from calling them gas giants because really only Saturn is truly a gas giant, predominantly made of gas. Notice that deep down in their cores, they contain quite a bit of ice. Now, most of that is water ice. Okay. But also the weird thing about this, hard to understand, is that that is high temperature, high pressure ice. It's able to maintain solid form because of the incredible pressure from above. But that's not the point of this, so let's just keep going. Now, Earth on the surface does have some ice in Antarctica and in Greenland, and depending on the weather in the northern hemisphere, in the mountains. Mars as well has ice caps that expand and contract with the seasons. Some of the ice on Mars, however, because Mars is significantly colder, is actually carbon dioxide, is actually what we call dry ice. Now, Venus is our sister planet, very much like the Earth, but much, much hotter. So way too hot to have any ice caps whatsoever. Okay. So here on Earth, the way we expect things to go with at least water is that it will be ice until about 0 degrees Celsius, and then it'll be liquid until about 100 degrees Celsius, and then it'll be a gas above that. But interestingly, that's not what happens on Mars, because Mars has a lower atmospheric pressure, just below what they call the triple point for water, right here. So on Mars, what you get is when it's cold, you get water ice, and then when it warms, it turns directly into a vapor, it sublimes. So basically, you go from solid to gas. Now, that's something you might want to call dry ice, but here we're talking about water. Remember, solids are where the molecules, they are moving, but they're moving slowly enough that they can really cling to each other, form a nice crystal. When they get more energy, what we expect is for them to turn into liquid. But what some people don't realize is that you only get liquid when there's enough pressure pushing down on the surface. You sort of have to have a lid on the liquid, like an atmosphere above it pushing down. But then eventually, when you give it enough energy to separate the molecules from their clinginess, you wind up getting a gas like water vapor. If you were to continue adding more and more energy, well, eventually it would break apart the bonds and then strip off the electrons, and you would wind up with plasma. I never want to forget to mention plasma because it is the fourth state of matter, and that's what you would find, for example, in the star, in the sun, and in Rao itself. On the other hand, there's what we call dry ice. Now, dry ice on Earth is carbon dioxide. But as I just mentioned, if you were a Martian, you might call water dry ice. So it's really a matter of perspective. Now, here on Earth, because of our atmospheric pressure, carbon dioxide goes from being a solid directly to being a gas because we're below its triple point. Now, even though Krypton is a higher pressure than the Earth, maybe it's not 5.11 times the pressure. Maybe it's just shy of it, like 4 or 5 atmospheres. The reason I'm expecting the atmospheric pressure to be higher doesn't necessarily go along with the fact that it's a bigger planet with more gravity, but you would expect that. Now keep in mind, you can fly in the face of this with Venus, because Venus actually has less gravity than the Earth, and it's got a much thicker atmosphere. But I'm just saying, if you had to make a guess, you would expect the atmosphere of Krypton to be, denser than the Earth's with a higher atmospheric pressure. But as long as it falls below the triple point, let's say 5 atmospheres or less, then you would still have the same thing happen, where carbon dioxide would go from a solid directly to a gas. It would sublime. If, however, you had a planet with more than 5 atmospheres, well then, at some temperature ranges, you would have liquid CO2. You can have that. So then maybe you would have lakes and oceans of carbon dioxide. That is possible on the surface. But we don't see that in the movie. I've never seen that in the comic. So I'm going to say probably Krypton is about 5 atmospheres. Carbon dioxide isn't as clingy as water, not very polar. It's a non-polar molecule. And so they don't stick together too well, just a little bit of energy added to them because we don't have enough pressure to hold it in liquid form, pops it apart into a gas. That's called sublimation. And going the other way, going back to a solid from a gas, is called deposition. And then, of course, adding more energy would rip apart the molecule and strip off the electrons, and you get a bunch of ions and electrons. Okay, so that would be plasma. I never want to forget to mention it once again. Mention it twice. So what am I suggesting that Jor-El's calculations were? Well, it could have been based on fluctuations in the temperature of their star, the red star R.I.P, and then looking at the structure of the planet Krypton, maybe some of those crystals are silicates, maybe some of that ice is water ice, but I'm guessing that it was cold enough that a lot of that ice was dry ice or carbon dioxide. And so looking at a pressure temperature diagram and where the planet was heading, he concluded Jor-El must have calculated that the carbon dioxide would sublimate away, destroying the structure of the planet. And if there was enough carbon dioxide that was generated, let's say it wasn't symmetrical on all sides of the planet, but was coming out more on one side than another, well, guess what? That would also help support that other scientist's suggestion that that could alter the orbit of the planet. Because if you have a jet of gas coming off one side more than another, that could have a slight effect on altering the orbit. We see this sometimes with comets. Okay, comets are of course usually much smaller bodies than planets, but because they contain so much ice, when they come into the inner solar system, a lot of their material will sublime and it will form a jet. Now, the jet isn't usually that strong, but from a whole planet, who knows how big it could be. And then, so imagine when Krypton was going through this phase, it would have appeared to be like a giant comet. And then that could have also altered the orbit. But then if you look at the results, who turned out to be right? Was it Jor-El or was it the other scientist who didn't believe him? Well, it was Jor-El. And luckily, he had that technicality to save his son Kal-El, send him to Earth, and defend Metropolis and America and, oh yeah, the rest of the world a little bit as well. Now, I know they've retconned this in later years. They've done all kinds of wacky stuff, as they do in comic books, that contradicts the original story, alters the original story, and a lot of what I said is clearly based on the movie perspective. Plus, is Superman really the only survivor, the lone survivor of a destroyed planet? What about Supergirl? What about Krypto, the dog? What about the shrunken city? I mean, come on. So there's all kinds of like exceptions to this, but I don't want to go into that. I think that was enough. So let's look at the time. I think we've said enough about this. Thank you very much. That's it. So now we know my speculation about what Jor-El's calculation actually was about.